So one more time, hello students. The topic of today's lecture is Introduction to Medical Image Analysis and Processing. So really, with this lecture, I'm going to provide some basics about importance of medical imaging and some technological background, physical background, etc. With more emphasis on topics related to information technologies and information system which is involved in medical image acquisition, processing and management. In fact, you will met these topics many times. Specific medical clinical courses. So really today it's really only introduction, and specifically even I am not a physician myself. My area of studying is computer systems. So again, we just have to define what is medical imaging at this point, understand that it's multidisciplinary fields, consider some approaches for imaging acquisition, analysis, and processing. So yet another reason why do we have combined course with biophysics. As I said, I will make emphasis on analysis and processing, and then on information system and standards involved in medical image processing. So first of all, we have to define what is medical images in general and consider some few classification of types of medical images and also related modalities, types of information we gather from medical images and so on. So from very long period generation, imagine essential aspect of medical science for visualization of anatomical structures and functional metabolic information of human body. But only relatively recently, no more than 150 years, then physician had, let's say, with some advanced technical capabilities to, let's say, external and then internal images of bodies and their parts, and that after that they have chance to drastically increase quality of diseases making and treatment planning and providing medical care for patient with this. So in fact, it's all that's because of development of imaging instrumentation, which inspired the evolution of new computerized image construction, processing, and analysis methods for better understanding and operation of medical images. So at this point, I'm speaking about the second stage, which had been started with development of digital computers after Second World War, and which allow, let's say, which recently bring us to intelligent or model-based quantitative image analysis approach, which have been explored for computer-aided diagnosis to improve sensitivity and specificity of radiological testing with medical images. So generally, when we understand principles and involvements of medical images among other fields, so every time we have to start with our existing knowledge, with that's a starting point where we have basic understanding, basic knowledge on anatomy, understanding of what we are going to visualize, and then next important points, we every time have to turn to physics. So only physics give us principles and approach to retrieve of image and keep it permanent, for example, store it on yearly on films, modern time in digital form. So physics, like as we talk about refraction of visible light or registering of attenuate energy like X-ray, like X-rays. So all this capabilities comes from physics of imaging. Based on physics, we have to turn to engineering, which could give us instrumentation to necessary diagnostic device capable for perform image acquisition. And here is we come to modern time, to modern level. With digital computer, we can digitize and process of already recorded medical image and apply all existing knowledge to perform analysis, visualization, if possible and necessary. So simulation, modeling, some kind of 2-3-dimensional reconstruction, etc. And based on all these features, modern physician have to make some kind of diagnostic decision and create treatment plan apply to patient, and then actually cycle have to be repeated again, loop have to be repeated again, and might happens we will need another image of another type of which based on another physical principles and so on. So, and when we talk about process of retrieving of medical images, so large number of knowledge from different area and efforts of different sides had been necessary to create all that mighty equipment that's available for modern physician in current times. So, and here is just again summarize of previous. That's medical imaging, modern diagnostic radiology. It's evolved as a result of significant contribution number of different disciplines from basic science, physics, engineering, medicine, and so on. So actually, a number of computer vision methods have been developed for a variety of application, image processing, segmentation, analysis, reconstruction, and recognition, and so on. So in fact, the logical science in the last maybe even a little bit more, 3-4 decades have witnessed the revolutionary progress in medical imaging and computerized medical image processing. And actually, modern time, we have numeric approaches which allow for physician to retrieve different kind of medical images which visualize some specific elements, components of human bodies. And here is just listed few modalities, few approaches, like them conventional tomography, or so even if we're talking about computer tomography, which actually in details will be considered later in this lecture. But even here right now, it listed at least 4 different type of computer tomography, like conventional, SPECT, PAT, MRI, including functional MRI. So all this, and just when we're talking about tomography, we will have number of solutions available modern time, which differs in mostly, first of all, physical principles of image acquisition. But also this way we have to distinguish like ultrasound imaging and various modern approach to retrieving even microscopic images, fluorescent microscopic and other approaches, and so on. So we have quite big number of approaches, modalities to retrieve different type of medical image, which will emphasize different features of human anatomy or functional And if we continue speaking about modalities, so another criteria to distinguish the way we retrieve medical images, it will be energy source. Like we use external, we could use external energy source to illuminating object we are interested in, body or part of organ. We can register any internal changes or combine both. So most common things, it's of course external illumination, starting from conventional photo, and then, which is most important, into various way of X-ray imagings, from conventional X-ray and up to different type of tomographies, of course ultrasound here related, same transmission, transillumination, optical imaging, and so on. When we talk about nuclear medicine, that's only a very specific solution, like positron emission tomography had been listed under this category, and various combination like fluorescence imaging, impedance imaging, and MIB, which combines internal and external sources. So that's about the same. Yet another classification of medical imaging is electromagnetic radiation. So practically humans' eyes have capabilities to see very narrow band, very narrow area within general electromagnetic radiation spectrum band. So we have limited here. And if we want to see more, we need to use different wavelengths, frequency, different energy levels for illumination of human body in order to retrieve some internal structure. And here is where is the place like we have for long wavelength and relatively low frequency energy. It's there like MRI images, and we have X-ray, gamma ray imaging for high energy and high short wavelength and high frequencies. So here is but what is actually modern medical images do? It's converting measures made in this invisible for us physically areas, converting into visual spectrum. So, and here is again yet a little bit another representation of the same way when we have increase wavelength or decrease, and depending to ionize low high energy wavelengths we have, magnetic spectrum we have. So here is again different types of images we can retrieve this way, and which could be used or for visualizing or mostly for anatomical information like X-ray, MRI, optical images, or to visualize functional metabolic structures and actually performance of organs and body parts. So here is we have different proton positron emission tomography, functional MRI, ultrasound, fluorescence images, and so on. Okay, so after this basic introduction about importance and classification of medical image, let's the second question in our lecture about process of medical images acquisition, analysis, and processing. So first of all, we have to identify general biomedical image processing and analysis system unit. Then we find to understand what is digital images. And then like few points I will spend about types of transmission imaging devices which use it to perform acquisition of medical images, and more attention will be passed to some background theory for image analysis and processing. So generally, when we talk about any kind of medical, not only medical, in fact, imaging device, it's have to consist modern computerized imaging device. It's even applied. So this diagram, in fact, even could be applied to camera in your smartphone, in fact. So we have, first of all, image acquisition system. In case of diagnostic equipment, it's have to convert biomedical signal or radiation carrying information of interest into digital image, or at least digital signal. To be correct, an image acquisition system at this level, it produces rather digital signal than digital image itself. Digital signal which represent digital image, but not image itself. Then, in fact, computer system unit or application software, for example, if we talk about some embedded system, because very often those units are embedded modern time into acquisition system. So still used to store image and further processing. And only at display unit, humans couldn't see something, because in both this level, we are talking about digital representation. And only at last stage, we have some visual form, visual things to be observed. So when we talk about, before we will be able to move further, we have to make some notes about what is this digital image. First of all, image itself, and then digital image. So when we talk about any kind of image, mathematically, and here is important point, we have to see images as two-dimensional, as flat two-dimensional signals. Flat two-dimensional signals. So, and any kind of image consists of different picture elements or pixels. And it's not only I think you hear term pixel, and every time it's referred to digital image. But we have to understand that's actually any kind of image, even those we could have could call analog, they are also consist of pixels, and even paintings, if you take a closer look, they composed of dots of different color, and those dots, they are exactly pixels, just that's physical pixel. And so in this case, flat two-dimensional image is two-dimensional signals, and value intersection of XY coordinates for these signals. It's give us pixel value at that point of image, like kind of color, for example, if we're talking about color image, or intensiveness of grayscale, if we talk about grayscale image. Again, at this point, I don't spoken about digital image. I'm spoken about general what is image, how we recognize it. And when we talk about three-dimensional image, so it means exchanging of two-dimensional sequence of two-dimensional image through time. So in this time, let's say we come to the mathematical idea of motion in a video, motion or video. actually. So every time we have to keep in mind that picture image composed of pictures, any image, and actually mathematically at given xy coordinates, we have function which give us information about pixel characteristics at z coordinates, like intensivity value or colors, etc. So correspondingly, when we turn to the idea of how to digitize image, so as conventional image composed of pixel, we need device which will be able to register changes of energy which is come from environment and produce some electrical response, some electrical signal, which will be depend to that amount of incoming light, which is measured, which composed by protons, stream of protons. So here is we talk about charge couplet device had been developed decades ago and allowed to create which allows to create matrix, sensitive matrix array, which is actually used to recording digital images of any type, no matter if you are talking about visible light like camera in your phone, or if we were talking about device which is used to registration of X-ray transillumination. They all technically very similar, difference only in details of CCD device, which has to be tuned to different wavelength. So that only here we have difference. So again, what single CCD device units do, it's in response of illumination by some external energy, it's generate some electrical current. And if we want to create image, we have to make a sample or matrix of many of this device. And here is important point if we talk about, if we want to usually conventional such device adjusted to only one relatively narrow frequency band, so it could produce only monochromatic image. And if you want to create color image, for example, visible light color image, we need number of device adjusted to different wavelengths. So there at right bottom part, here we have some kind of wire arrangement of color filters, which will pass through only specific wavelength to our recording device. Okay, so once we are given some voltage level from pixel, so after that it has to be processed by digital computer or digital DCU unit in order to convert digital representation of this pixel. And after that we will be able to talk about digital image. So here is practically again how any digital image have to be created. We should have that array, sensitive array of sensor CCD devices, and it has to be illuminated by using external source or sunlight. If in case of conventional camera, that's some sun element has to be illuminated, or it would be X-ray source which pass through human body, then or some imaging system, some system of lens or deviation coils or something like this, distribute that image distribute rays over entire sensor array, and so being illuminated by different amount of energy, each cell of the array, each digital pixel produce corresponded level of voltage. And depending to intensiveness of this illumination, so different pixel produce different levels of voltage, so we can see image. Now, from this picture have to be obvious major problem with digital image, the so-called array size or resolution. To get better image, we should have smaller sensor. Each sensor has to be smaller and number has to be as big as possible, as large as possible. So here is we have, and every time we will have some like deviation from original force. So because as input we have continuous signal, and as obviously that some of this sensor elements being illuminated not enough below threshold and they don't generate any electricity in response. So our digital image every time it's a result of so-called sampling and quantization. So again, as I said, when we illuminate sensor array, they start triggering emitting electrical signal after some specific threshold. And if our signal for this pixel element below threshold, it will generate nothing. So we will have this like squared representation of our object. So it's low resolution. It was like a very big problem for decades. Quality of digital image, it was very low. It was where square-like forms until relatively recent time, when it became possible to create very small sensor elements and create matrix large enough to generate high quality images. So in fact, what do we have, how digital image has been formed? So here is above, again, we are talking about mathematics. Here is above, we have original matrix of continuous signal which had been illuminated over each one sensitive element. So here is we have matrix of continuous signal for each pixel, and below we have its digital representation, some quantified value, single value which reflect some specific level of this original continuous signals. So that's actually reason why sometimes modern time, maybe not quite often, but before it was very often, why sometimes when we're talking about digital image, they has been called as matrix image, because they are formed by matrix of pixels, by matrix where each element represents information about particular pixel at given coordinates. So our digital image is this one matrix. And here is absolutely obvious consequence. So major points you have to understand. When we talk about any kind of operation and with digital image, it always is matrix operation, matrix algebra operation. So matrix algebra, it's absolute background, it's absolute essence of any kind of digital image processing operation. no matter if you efficient or not, it is. And here is again, like to finalize, made this all together, how it's actually practically look like. So first of all, we have analog image at top left, which is that energy which has been illuminated over sensor arrays. We have components of sensor like what is single cell could produce some specific voltage. We have analog way when we have like binary that's binary equivalent, which could be made for this each one pixel. And here is what do we have at the end, bottom row. Digital sampling, how we can, this small area will be look like, how it will be illuminated over sensor elements. And at bottom right, we have quantization results, numerical representation of this input analog energy flow. So this things at right bottom corner, that's exactly what will be stored in digital computer and what will represent this small square area of an analog image. Of course, practical format of storage will be not exactly binary matrix, which is quite inefficient way. Usually it will be encoded in some specific digital image formats, like JPEG or TIFF or so, but it's like less essential points than understanding what it is digital signal in its nature. Because again, if we are going to make any transformation, any change, any measures for this image, we have to deal with this matrix. And particular software do it. Okay, so now I will turn into section which is related to transmission images, but I will pass through this section relatively quickly because it's rather related to medical biophysics, and you might be even already given information related to these topics, but still I have to touch it as it's critically important, a component of medical imaging. Creating. So I will a little bit speak about ways how digital medical image could be obtained. So first of all, through transmission based on principles that radiation is created and passed through human body. And in this way, working everything starting from X-ray radiography, but not only, because even microwave infrared images, they obtain it the same way, and part of optical images as well, because they work on reflection from human body and not everything being reflected. So obviously about 130 years ago, principles of registering of X-ray has been created, or Konrad Hen, or sometimes it's spoken that Ukrainian scientist Ivan Polui also related to this. No, Konrad was more fortunate to patented his invention. So, okay, we will put him as discoverer, which he was given Nobel Prize in Physics Obviously, initially for decades, X-ray images had been registered by using films, which is sensitive to this kind of radiation, and so like this one, and it will be possible only to create two-dimensional images. Then about 1960s comes the idea of creating computer tomography and creating tomography images. Generally, it was actually also a long way, and before it was become possible to create computer tomography, then it was necessary to pass through some quite significant achievements, not only in physics, but in other areas. And let me show this in 1 minute. So generally, how to understand what is tomography itself. Graphic representation good or twice and implies formation of two-dimensional cross-section image free of blurring from structures not in the plane of interest. And computer tomography, of course, it's formation of tomograph X-ray adsorption coefficient by methods of reconstruction from recorded projection. So in fact, if simply put, under tomography, we have to understand of reconstruction image in projection, which is perpendicular from plane of observation, based on visible projection. So actually, those achievements had been made by two scientists, computer expert and physicists. They working on this for about 7 years, win Nobel Prize for this. Initially, of course, it was spoken only to generating number of two-dimensional cross-section image. Later, with development, more advanced computer systems become possible to reconstruct and visualize three-dimensional anatomical models for this. Later, also, it was become possible to add some visualization of not only hard tissues like bones, but even more softened tissues. The idea is again of formation image object. It's viewed from number of different angles, and then cross-section image of it can be computed or reconstructed, as I already said. So here we have topical projection image, direct, what we see directly if we will just make an X-ray, and actually if we will pass through this, when we will make number of such section from under different angle from the same object, and pass through necessary computer software, we will have ability to reconstruct image like this here shown in the bottom. So, and here is important notice how it's become possible. First of all, as I already said, is physical achievements, invention of X-ray imaging. Then what were critical is mathematical achievement, so-called radon transformation, which provide necessary mathematical tool to reconstruct image by using its projection information only. And then achievement in computer development, so creating powerful enough computer which allow to keep at least some fraction of digitized X-ray images, and at the same point which have capability to execute algorithms which implement not even radon transformation of itself, but so-called reversed radon transformation, inverted radon transformation. And all these things had been necessary in order to develop of CT. So here is we talk about always this way: physics, mathematics, engineering, and computer system development. So those steps are essential, they are all necessary. Okay, so here is shown example of first generation of tomography, which required a number of moving parts to eliminate patient at the different angle and retrieve all necessary information. But even in modern tomography, it's going same similar way. So the idea right now, and some brief points about mathematics, idea of radon transformation, that's in fact what is radon transformations give us this function which describe projection of image. But when we talk about, so it's, in fact, it's results of X-ray or tomography scan. So we got value of this function, not function itself, we got value of this function. And if we want to, our goal is to reconstruct original image, this one, visualization of the source. So we have to invert radon transformation. And as you can see, it's all based on matrix operations. So when we talk about direct images, it will look like something like this here at left side, 90 projection for this object. And to recover inner structure, we need inverted, and so we more projection we have, better our image will be. And here is we have 18, 36, and 90 projection. 90 projection, and actually so-called Fourier transformation help with redirecting of radon transformation. As you can see, quite advanced mathematics. Yeah, that's what actually our final outcome is here. And so with inverted transformation, we will receive function which will represent for us original image. And actually it will be this one. So here is this integral have to be solved in order to rebuild our image. Okay. So here is additional steps. We have two steps processing, few interdimensional mathematics with Fourier transformation along different angles, then revert apply inversion of Fourier theorem, and so here is that steps which is necessary to reconstruct original image. And here in yellow, it will be our final result. How we can reconstruct this? It's a reconstructed function, like projection function, results of radon transformation, and reconstruction function, results of inverted radon transformation. As you can see, both represent advanced mathematics, and obviously it's required quite significant computation power. But result will be like this one. So here is we have original object. Here is we have so-called sinogram, or visualization of direct radon transformation. And here is we have reconstruction by using inverted radon transformation at the right side. And here is after that way how possible to construct at least two-dimensional cross-section image from computer scan. Actually, by this time, probably not fifth, but sixth generation of computer tomography already available. Both has no moving parts. Now we need just seconds, fraction of seconds for scanning in comparison to sometimes dozens of minutes in the past, and we have much less energy exposure patient to attenuation radiation, which is not health things at all. More or less how it's work in modern time. We have target rings, we have some series of deflection coils which deflect signal, and we got our signals. And now, in modern time, we have some number of continuous tomograph which provide a continuous scan which allows to retrieve not only two-dimensional cross-section or stack of CT scan images, but actually actual three-dimensional visualization of it. So here is so-called slice-by-slice scanning or spiral volume scanning, which allow for us to reconstruct three-dimensional images like as given at right, and even create dynamical visualization like this one. So again, we have to understand that all this, it's in fact not original images. It's all this a computer models which is reconstructed through mathematical transformation like inverted Radon transformation, Fourier transformation from original projection information. And quality of this image, and that's only depends to quality of our mathematical models. Now, very briefly about other kind of tomography like MRI or PET or SPECT. So, fundamental difference for those types of tomographs is physical principles. How do they, what kind of signals they do register, what kind of energy they react onto it. But from from information technology viewpoint, they are all the same, because algorithms which is involved in image reconstruction almost exactly the same as in conventional computer tomography. So here is we have things when it was absolutely different principles, absolutely different physics, but computational approach are the same. So just MRI much better works with soft tissue because of principles that it's working like. So it's good for soft tissue vessels. It's good to visualize dynamically metabolism process and so on. Like it's allowed to create angiography as even independent specialty for studying vessel and so on. Same idea with nuclear medicine image, which register a distribution of radioisotope, which are distributed within human body. Also very useful to visualization of metabolism of function in organ structure by an imaging. So that's those SPAT and PAT tomography, single proton emission tomography had been used. So again, we have quite significant difference in physical principles, how we have to register this difference is radiation emission, but again, approach to reconstruction of image, same as in case of CT. So just what we can get with this. And relatively recent approach, it's about less, it's in active development for about less than 30 years. It's create of combined images, which combine different modalities, different type of images, like combine MRI with PIT images. So again, it's pure synthetic image and we have to trust mathematical model. We have to ensure that our mathematical model and understanding of anatomical structures and functional process are correct in order to consider combined image as trustful. So a little bit different principles used in ultrasonic imaging. It's propagated into patient from transducer placed on skin and backscattered echo signal recorded. Non-invasive, much cleaner, safe comparatively to attenuated images like CT scans and so on. Usual components of ultrasound image meshing. Again, so only quite recently compared to case of CT scans, it's become possible to create three-dimensional and even dynamical ultrasound images. For a long time, it was only two-dimensional images, and here is problem with why it was like such a long way compared to CT scan. They were already available, already capable of three-dimensional visualization, and ultrasound still remain two-dimensional. It's problem with frequency and amount of information. CT ultrasound is high-frequency device, so it's generate enormous amount of signal data, and it was necessary to years of evolution of computer systems. They become capable to acquisition such stream on the fly and made on the fly transformation compared to CT scan, where it's first of all stored relatively small amount of data because quality number of pixels even in modern computer tomography relatively low, even compared to smartphone camera. So it was necessary years, decades before it's become possible to make a construction for ultrasound image. Okay, now we will move into again question which is related to information technology and to the process of to questions which is related to image processing. So we will concentrate at this area, processing, which is actually included few steps. If you will take a detailed look into processing stages, it will involve few steps like pre-processing, segmentation, detection, analysis, and diagnosis. So, and part of those, like except pre-processing, they are useful in case of possibility of automatic decision-making based on images. Like if we will talk about organize the structure in different way and take a look about more details. I to get more details on this. So here is we have stage of formation when we perform acquisition of our signal and convert it into digital representation. Then basic enhancement, which included the optimization, transformation, filtering, signal calibration, registration, etc. In fact, at this point, after this stage, it's possible to make one of three tasks, like or immediately visualize it. No matter if we talk about two-dimensional visualization, actually it's possible directly after enhancement, or if you want to use three-dimensional visualization, we need to pass through steps, which is a little bit similar to the computer games ones, like reconstruction of surface, illumination, shading, and display. So here is we need three-dimensional visualization. But at the same point, immediately after enhancement, it's possible we have actually ready to use medical image. I mean, two-dimensional medical image, of course. So it could be, say, and manage it as is, in case, for example, if we're talking about conventional X-ray. But what is most important and what is most useful in modern time, it's automated analysis. I mean, they are specifically about automated analysis, and it's involved feature instruction, segmentation, classification, interpretation, and measures. So again, for long years, it has been objective for physician, but in modern time, it's possible to be automated, and it's possible to achieve some results automatically. And just again, I remind that nature of almost entire all this transformation, it's matrix operation. And if you want to make any change, scale, rotation, translation, so all this, it will be different type of matrix operation. So here it is. Again, no matter what we're talking about, selfie on phone or X-ray images or computer tomography. So pre-processing of image involve usually filtering, denoising, registration, and image enhancement. So for example, if we talk about creating usage of different, even if we talk about grayscale image, depending of number of quantification, we could get different quality of image from monochromatic, low-level quality monochromatic at bottom right to relatively high quality grayscale image top left. Major algorithms which used in pre-processing, it's like median, mid filters, wavelength-based denoising, wavelength-based image registration, and so on. So here is, in fact, what is filtering. It's idea that output fixed pixel of our image will depend for few pixels at original image. So here is how it could be transformed. And the question is only what kind of formula will be used for filtration, like it's mean filter, Laplacian, nonlinear transformation. It's different approach. Again, and for example, obviously, modern time physician, no need to do it manually. Yes, of course. And there are plenty of different solutions. In fact, each one diagnostic equipment which produce medical image obviously has built-in features to perform filtering, let's say, on some predefined levels to make some basic adjustments. It's like obvious choice for developer. But at this point, I'm going to talk about some universal solution, third-party application, which is useful for image processing. And one of the interesting things is ImageJ, free open source project dedicated to manual or semi-manual, because it's our contain things for automation, processing of medical images for deep analysis. Again, it's tool for perform scientific analysis of medical image. But what it's actually do, it's replace all this mathematical formula with conventional commands that physician no need to learn. This mathematic, no, rather not physician, rather medical scientist. In fact, no need to learn these formulas, but have to understand idea behind these formulas, and this way possible to apply some kind of filter, for example. So, and here is why it's necessary. We can get to feature enhancement by filtering and like identify, will be able to visualize some potential pathological changes with given images, like this one. This could be feature enhancement, could be used for identification some elements on mammography images. So here we use adaptive contrast enhancement algorithm had been applied to made emphasis on those structures. Okay. And here is different histogram equalization and so on. In our next step after filtering, it's segmentation, or exactly delimitate object once they are detected. So in this case, it's possible to identify closed area, which usually represent some tissues, organs, vessels, and so on within human body, like this one. So here is algorithms dedicated to automatically identificate such objects. Yet another application available here is things actually segmentation filter. It's also we use term filter, but this time it's dedicated to create segmentation task with so-called MIB application. This time developed in Germany, MHA, it's United States solution, and also allow to process images without studying symmetrical features, but still required understanding of algorithmic process. So here is there are multiply algorithms, segmentation algorithms like means fuzzy, narrow fuzzy. Modern approaches more and more often use neural networks-based segmentation, so-called convolution neural network, for example, or VNet in case of three-dimensional images, and so on. So, in fact, what is capabilities of this approach? It's to create image like this, it's to separate different specific organ tissues and create their combination from original image and get into something like this. So detection. Again, next stage after segmentation, it's find location of object of interest without prior knowledge about their location existence. So, most common things as attempt to identify some potential pathological elements here, or like things which should not be here, for example. Simply put, so when we have to know that something like so-called normality and looking for things which is deviate from normality in a given location or so. So, but also it could be useful for automatical identification of anatomical elements. So helpful methodology in detection of abnormalities, its usage of multimodal images when we combine different sources like PET image, CT image, and here is we have ability to easily detect potential inclusion. We have like what we will have there, some active consumption of active physiological process observed here on the PET image, active growth of cells and so on. So, which is not such obvious on CT images, and combination of those give us that's very distinctive hint about potential very active pathological process. And similar things with PAT image or using, for example, ultrasound imaging of our retina to detect diabetical processes, diabetical retinopathy, and so on. So actually, like past, present, and future of medical image processing. So I will only concentrate on future by having tools for creating multimodal image and multidimensional image, by having tools for automatic segmentation, classification, and management. We got ability for CAD or computer-aided diagnosis process being implemented. We have ability to use computer system, include modern with artificial intelligence to automatically create intervention planning, treatment planning, and so on, and create computer, even apply computer-aided surgery or modern robotic surgery techniques. I have spoken previous lecture. I have mentioned previous lecture, not spoken, actually only mentioned previous lecture. So all these achievements are results of ability to manage multidimensional, multimodal images. Okay, and at this time, I'm going to come to the final question for our lecture about PACS and DICOM. So, about tools which allow us to which allow physician to manage, effectively manage of medical images. So first of all, if we talk about PACS, we have to understand it's special kind of computer information system, picture communication system, which is computers or networks dedicated to storage, retrieve, distribution, and presentation of medical images. And usually they were features tightly related to utilize DICOM or digital communication medicine or international standard dedicated to manage medical images. So in fact, PACS has to replace hard copy images like those printed on files, and it's offer many capabilities for physician, like remote access of image, automated processing, and even delivery for telemedical delivery of images for telemedical consultation, and even usage of in distance education and so on. And also, of course, exchange with another medical information system, access from any physician workstation in hospital to hospital information system, and so on. So practical implementation could have some variety. Usually, yes, we have some central storage and application software which allow for access to local network or even to internet with all necessary security components in place. So general, what do we have? The idea of PACS is collection of all type of images which is available within facility, and then provide access for physician. How it could be look like? It's all could be or something like specific software or part of general electronic medical records hospital information system. It depends for particular vendor, for particular system solution, and so on. And a few words about DICOM. It's actually standard for handling, storing, printing, and transmitting information in medical image, and includes file format and network communication protocol. In fact, probably all modern medical diagnostic, medical imaging equipment has capability to generate DICOM images. On the other hand, it's actually not medical imaging equipment, in fact. Moreover, all modern diagnostic equipment have features to directly communicate with hospital information system through computer network, wired or wireless. That's nothing unique right now. And actually, DICOM ensures that no matter which vendor we choose to buy our diagnostic equipment, no matter of model we will use, they all must be compatible. They all will produce image that could be accessed from any physician workspace and accessed from like general EMR, HR software, and etc. So is given organization which is responsible for maintaining DICOM, National Technological Association. Okay, how it's work in case of if we have some non-DICOM equipment still available in hospitals, still operable, we should have some kind of workstation which allow to register some digital data stream or analog stream, convert into DICOM format, so add necessary field value, and then send to central network communication. Actually, important things on the DICOM that it's groups information into data set. That's file of an X-ray chest actually contains patient ID and information, general information about patient, equipment, physician, hospital, etc. So we have a large number of attributes which have to be filled in order to have spoken that our DICOM file is comprehensive and fully functional. And then another section of DICOM, it's actual image. So it's combined image with data set about image, which have to depict all aspect about what's kind of image. So here is actually infrastructure of DICOM. It's very broad, but have to understand that physicians usually work at this level, so they usually have access to like only file-based DICOM, which is represented in some storage on computer hard drive or some medias, even like CD, flash drives, and so on, and useful for manual exchange. But actually, most important part of the DICOM is that things at left side, which provide major DICOM features, so ability to exchange between device itself. And here is some number of DICOM viewers, free, paid. So there is a lot of things. So what is most important? It's that service information which could be available. But as you can see, what is main problem with DICOM? Lack of annotation. They contains necessary fields to input data, but unfortunately, like in this case, it's very often that physicians don't have time, for example, simply don't have time to fill all this. And as a result, we might have DICOM which is not fully filled with all necessary data. Okay, that's actually everything I want to talk about, my kind of introduction for medical image analysis and processing. Thank you for your attention. Goodbye and have a nice day, and we will meet at practices.